This last section is about logistic growth models, and that's bonus. So this is an optional section. You can do it if you want to, and I will give you extra credit. So here's an example of logistic growth. The mathematical model is limited. So this is where it looks like exponential growth at the beginning and then it levels off. Notice our base and exponent are in the denominator of a fraction. So this is just two different ways of writing those logistic growth models. We can use f of t or a, it doesn't really matter. So a, b, and c are constants. C needs to be greater than 0 and B needs to be greater than 0. Let's take a look at some of those. On this slide we have examples of exponential decay, exponential growth, and we have some logarithms here also. So a logistic model is going to have the property that it's going to grow really fast just like an exponential function does, but then it kind of levels out. And logistic function models tend to be a little bit more realistic for modeling longer term population changes. Exponential growth does happen in the real world, but over time nothing's going to grow infinitely because there's always some kind of limit to the environment. Even with rabbits or bacteria, at some point they run out of resources and there's some kind of level carrying capacity that is reached and not surpassed. So let's look at a couple of examples. So this logistic growth function here describes the number of people, so f of t is number of people, who have become ill with influenza, so that's what it's describing, and then t weeks after its initial outbreak in a particular community. A, how many people became ill with the flu when the epidemic began? So that would be like T0, so the first day of the outbreak, when no days have passed yet. So think about what would be our number if we plugged in 0 for t. So just think about that. F of 0 would equal, we've got 100,000 in the numerator, and then we have 1 plus 500 e to the negative t. Well, we know that's going to be 0. Negative 0 is just 0. What would this e be? Well, anything to the 0 power is just 1. So basically what I have is 100,000 divided by 1 plus 500, and what we get is about 20 people. Part B says how many people were ill by the end of the 4th week. So how many people? So we're finding that f of t, and they gave us the 4th week. That's our time. Remember, t describes how many weeks have gone by. So I'm going to use t equals 4 in order to substitute that into my equation. Got e to the negative 4. Plugging that all into the equation, let's see what we got. And I got 1,080 people. And then part C says, what is the limiting size of the population that becomes ill? We can do that problem without doing any calculation, and where we find it is inside that equation. That numerator number, that is going to be the carrying capacity, and so that number is going to describe the limitations of how many people can become ill. So that is 100,000 people. go ahead and try the bonus question if you want extra credit.